Okay, welcome to another one. So we are going to take a look at the post lab for four, which is the equilibrium, Le Chatelier's principle. So we did a couple of things in this lab. We did Le Chatelier's principle. We looked at the base reaction, which is iron complexing with the thiocyanate to give us this iron thiocyanate complex. So all of this stuff is aqueous, and if it forms the complex that turned red, in just the ion form, the iron and the thiocyanate, it just remained colorless. So any shift towards a redder color indicates more product. Any loss of red color, more colorless, fainter color, is going to be more reactant. We also did a calibration curve and some other stuff. But with that, let's just focus on the Le Chatelier's principle part. So this right here is our equilibrium. Whenever you're looking at Le Chatelier's, what you should do is you should always have the equilibrium handy so you can say, okay, how did it affect this? How did it affect my equilibrium? So these are all of the things that we added to check. Now, we have, when I added iron nitrate, really what I did is I added two ions. And this is always how it works. You're adding two ions. I add iron nitrate, although I did. I added iron, 3+ ions, and I added nitrate ions. And so we have to ask ourselves, do either of these appear in the reaction? Do either of these or both of these affect the reaction? So the first question is always easy. Do either of these two appear in the reaction? Yes, iron does. Iron combines with any thiocyanate present to form potentially iron thiocyanate. So it's essentially the same thing as the equilibrium. This is a common ion situation. So by having a common ion, it is going to essentially push it. Again, we're increasing the concentration of that common ion, 3+ equals a shift away from the addition. So we're going to see a shift to the right. So we see a shift to the right. And that's what you should have seen. It should get darker. Again, increasing this shifts it away. If I increase thiocyanate, we're going to shift this way. If I somehow got rid of one of these, it's going to shift towards the loss. So away from an addition toward a loss. So the next thing is nitrate. Well, it turns out nitrate is really boring. We can always ignore nitrate. Nitrate will always, if it ever forms anything that forms a strong complex, so iron nitrate, because it's strong, that will always dissociate again and essentially not affect the equilibrium. So there's the net ionic equation. So the next one, KSCN. Again, really what I have is K plus and SCN minus. Are either of these in the equilibrium? And it is actually the same exact reason, but just for, in fact, I can just copy it this time. It's the same exact reason as before, as the previous one, but instead of iron, it is actually thiocyanate instead, SCN minus. And there we go. So also is going to be a shift to the right. How does potassium affect it? Well, it turns out group 1 is always a strong electrolyte. So anytime you see group 1, you can essentially just ignore it. It's not going to affect it at all. All right. Next up. So now we move into the next set of situations. So I've got sodium and I have hydroxide. Group 1, I can ignore the sodium. So hydroxide, which one will hydroxide interact with? Well, we don't expect hydroxide to interact with a negative, so we can ignore that. It interacts with the iron. So iron, 3+ plus hydroxide yields what? I'm guessing you saw a solid, which makes sense. Actually, 3 hydroxides form iron hydroxide solid, a solid formation. Actually, by the way, this may have been, if you didn't see a solid, but it did shift, that would mean it formed another complex, which we're actually going to see for one of these other ones. But solid formation. So if we think about what's actually happening here, is this reaction occurs. The iron finds the hydroxide that we put in, and it forms this solid. So ultimately, what this reaction is doing is it is removing the iron from solution because it turns it into iron. Essentially, it turns it into a solid. So by decreasing the amount of iron present, we need to replace, because equilibrium will always be equilibrium, we need to go back and we need to create more iron, and the only source we have is the iron thiocyanate. So this will try to go back towards the reactants in order to produce more iron, in order to get back to equilibrium. And so therefore, it is going to be a shift back towards reactants. So ultimately, what's happening is we were removing the iron 3 plus, and therefore we're shifting away from the loss. All right, next up, same exact thing. We have silver, Ag plus, and NO3 minus. We always ignore nitrates because they're always strong electrolytes. And now we have silver. What can silver interact with? Well, silver is not going to interact with the iron because they're both positive. So the only thing it could interact with is the thiocyanate, and it does. Ag plus reacts with thiocyanate, SCN minus, to form that complex. You shouldn't really have seen a solid, okay? Because it turns out the Kf for this, it forms another complex, 1.2 times 10 to the 10th, is a really high value. Ultimately, what that means is any silver that enters will find thiocyanate and it'll pull it out of solution. So in essence, we have a decrease in the concentration of SCN minus equals a shift away from the loss. So we're going to get a shift to the left. So we have these other things in the reaction or in the addition that are kind of removing from our base reaction. So we always want to focus on this. How does it affect this? Well, the silver removes some of this, shifts towards the loss. The hydroxide removes some of this, shifts towards the loss. And that's why we see a shift back towards the reactants. All right. Next up, we have sodium. I don't care that there are two sodiums. Ultimately, it doesn't matter because group one does nothing. And we have an oxalate ion. So what happens here? Again, this is going to come down to what you actually see, but iron does react with the oxalate present to form a complex. Iron O4 with 3, two of those. Sorry, there we go. I'm not sure if this is a solid. I don't believe it is. This is going to be aqueous. I'm not sure. You're going to have to tell me what you saw, but it removes Fe3 plus, and therefore it is going to, because this complex forms. And because this complex forms, it's removing Fe3 plus, and I don't really care about the presence of that complex. The only thing I care about is that it's removing the iron, and that's shifting it back towards the loss. And the last one, again, sodium we can ignore. Fluoride can only interact with the iron. So Fe3 plus F minus yields FeF3. I'm not sure what you saw here, but this is either going to form a complex, but I'm pretty sure you're going to see a solid form. And again, that's removing iron from solution. So it comes down to what you have. You can always look up the Kf values of something to see if a complex forms. Generally with cyanide or with hydroxide, those are the types of things that form complexes. But ultimately, we should see these shifts because of the losses, and the common ion always shifts it towards the right in this case to get away from the addition that we had. All right, moving on. So, question 2. Would the addition of the catalyst have any effect on the equilibrium? Why or why not? The answer is no. Equilibrium, oh, sorry, I should say catalyst only affects kinetics. or effects, kinetics? Not K. In fact, the only thing that can affect K is temperature. Temperature is it. Temperature and yeah, temperature is pretty much the only thing that can affect K. So catalyst will not only affects kinetics. We will get to equilibrium faster, but we will not affect K. The only thing that affects K is actually temperature. All right, good. So what color does the visible? So I've got a couple of things here to kind of assist in this explanation. So in the 440 to 460 nanometer region, here is the colors. So 440 to 460, so about 450, halfway through, we have a blue violet-ish color, right? So ultimately what we have is we have blue. But your thing didn't appear, this blue, right? That was, in fact, a deep red is typically what we see when we look in that region, that 450 nanometer region. So what's going on there? Well, if we think about what is happening is light passes through and gets absorbed. This blue light is getting absorbed. And so what do you see? Well, you end up seeing the complementary colors. If you think about a black shirt absorbs all of the colors. So it appears black or the absence of color because the color has essentially all been absorbed. If you look at a white shirt, it doesn't absorb any color and it looks like it has all of the colors in it because it hasn't absorbed any. What happens when blue is absorbed, you're actually missing that color. So if you imagine that the blue is absorbed, all of these other colors are essentially appearing to your eye, right? So all of those other colors, which is predominantly going to give you the complementary color or the lack of that, the complementary color or is going to be this orangish reddish color. So that's typically what you see. The complementary colors are usually what happens or will be what happens when you have that. So you're missing the blue because it's getting absorbed by the substance and therefore you're seeing the only thing that's missing, which is everything else. So that's the idea behind absorption. And speaking of, let's talk about it from a molecular level. Provide a molecular level explanation of absorbance readings of the five solutions. So you saw the concentration increase as it proceeded. So what you have, we know that concentration increased for our five solutions. So if I take a low concentration solution, so I'm just going to put five of them in there, and I pass light through. One, two, three beams of light. Well, you're going to get a ton of light out. You're going to get almost all of that light out. So this is low concentration. Okay. So in terms of absorbances, there's very little absorption because the only thing absorbing the light are the molecules, are the iron thiocyanate molecules. So if I have 100, let's say, or we'll do, if I have three light beams in, you're going to get two out. So the light in versus the light out, we almost get the same exact light out. There's no absorption. Any absorption that does occur appears red. But if we increase that concentration and we add a lot more, now when I put that light through, I only have a very little light coming out. All of the absorbed light is appearing as red. That's why it's getting darker and darker and darker. But we are having more absorption, means the more appearance of red because I've got more of that stuff absorbing. So again, the idea is low concentration versus high concentration. The higher the concentration, the more absorption, the more red that you're going to see. That's the idea behind the molecular level point of view. All right, describe two ways to shift the equilibrium position towards the product. And we actually saw that above. If you look at one and two, I have choices. I can either, the only way to shift towards products are increase reactants, because that's going to shift it away from the addition towards products, or I can decrease products. because if I lose it, it has to shift towards the loss. There's no real way to remove iron thiocyanate from solution because we're forming it. So I can increase the concentration of iron, or I can decrease the concentration of SCN minus. Either one of those will get me, that's a three. Either of one of those is going to get me to an increased amount of product. Okay, so with that, of the parts you described in A, compare Q to K. All right, so before we even do that, let's write out our K. K is equal to the concentration of FeSCN2 plus products over reactants, which is Fe3 plus times SCN minus products over reactants. And if we actually look at our K value from lab, so the one that we actually got, the one that I had for my lab, and this is the one I'm going to use in the next video as well, is about 400. You may have something different than that. It kind of depends on the day, but it should be around-ish there, or should be in the hundreds anyway. So essentially what this is saying, in order to get this value of K, let's say that I had 400 thiocyanate ions, and I had one of the other two. This ultimately is going to lead to a value of 400 to 1 for products to reactants. And that is ultimately going to lead to a K of 400. Nothing should change this, right? I could add more solid in this case. I could add a bunch of stuff, but it's always going to shift back towards equilibrium. We're always going to get back towards that target. Okay. But we are going to focus on just the change in concentration of iron. So if I increase the concentration of iron, what's going to happen? Well, if I all of a sudden just toss a bunch of iron in, I am no longer at a K because I'm now at Q. So let's say that we were at equilibrium with 400 of my iron thiocyanates, and I jump from 1 to, let's say, I don't know, 100. I I multiplied the concentration of iron by 100. So I go from a concentration of 100, or from 1, because it was at equilibrium, and I can actually do it this way. I end up adding 100 times the concentration of iron. I've increased the iron substantially. Well, if I do this math, my Q value is equal to 4. My K is equal to 400. It's going to shift back towards equilibrium. In this case, Q is less than K. That is ultimately what the question is asking. Q is less than K, which makes complete sense. That's exactly what it's supposed to look like. We have to increase K. The way we can increase K is more reactants. I'm sorry, more products, less reactants. So what happens is I increase this, I decrease the denominator, and we get back to K. That's ultimately how what would happen from Q to K. Did either way described in part A change the value of K? Did we change the temperature? We did not. So no. Only temperature can change K. That's it. It's the only way we can change K is simply by changing the temperature. Temperature, temperature, temperature. In fact, I think you look at that next week. You should look at that in Lab 5. K is the only thing that changes. I'm sorry, temperature is the only thing that changes K. All right, moving on to the problems part. So we're going to do some calculation. So my information is based on a previous lab that I did with my students. So your information, you have to use the data, not my data, but the data that you got from lab. So a solution is found to have a transmittance of 0.091. A solution to have a transmittance. For this solution, calculate the absorbance. Okay, so we're looking for the absorbance and the iron thiocyanate solution concentration. All right, so the percent transmittance, or I guess the transmittance it would be, is equal to 0.091. It's ultimately for percent transmittance. this is going to be 9.1% transmittance. So step one, it is funny that I didn't even recognize it was percent transmittance when I did this, but so 9.1% transmittance. The first thing that we have to do is we have to convert this into absorbance because I know that my formula, I'm going to put it above. Again, this has got to be your experimental data, not mine. So your absorbance is equal to, so mine was 2084.1 times the concentration of FeSCN 2 plus 0.0127. Again, this right here is from my experiment. You're going to write down your own. This is from the Excel spreadsheet when you did a best fit line for your 5 calibrated solutions in order to get your, and y is equal to mx plus b is what you had. X plus b. So it should be a best fit line, a linear best fit line, giving you this formula. On the y-axis, you had absorbance. On the x-axis, you had concentration of FeSCN2, FeSCN2 plus, and that should allow you to get to it. All right. So with that said, we have the percent transmittance at 9.1% or 0.091. So first thing we need to do is we need to make a change. Absorbance is equal to 2 minus the log of the percent transmittance. This is the math that we use in order to go from percent transmittance to absorbance. So that is going to be step one. I'm kind of doing this real time because I usually do them ahead of time, but I forgot, didn't notice that was percent transmittance until now. So 2 minus the log of, looks like, I usually do this in Excel, by the way. So 9.1, I'm going to take the log of that. Boom. There we go. So 2 minus 0.959. So 2 minus 0.959 gives me an absorbance value of 1.041. Okay, so that's what we have. That was my absorbance value. And now we're going to plug that into the equation above. Now that I have 1.041, 1.0. So I am taking this and I'm plugging in this equation. 041 is equal to 2084.1 concentration of FeSCN 2 plus 0.0127. So I'm going to subtract the 0.0127 from this. 1.0283 equals 2084. Ooh. 2084.1 concentration of FeSCN 2 plus. Now divide both sides by 2084.1, and my concentration of FeSCN 2 plus is equal to, so divide by 2084.1, gives me a value of 4.93 times 10 to the negative 4, and this is going to be molar. So let's think about this. This is a very high absorbance, and that does make sense because my percent transmittance is very low. The percentage of light that actually transmitted was only 9.1%. 9.1% of the 100% of the light got through. So the absorbance value, and I think I've got to highlight that as well, is 1.041. Okay, higher the absorbance, the more absorbed light. Lower the percentage of a transmittance, the more light was absorbed as well, right? They're opposite each other. All right, so with that, the next one actually should be pretty simple. A solution is found to have a percent transmittance of 31.4, calculate the absorbance, and so we have to do it again. That's easy enough. Now that I have the percent transmittance of 31.4%, I'm going to plug that into the equation above. my absorbance equation. So absorbance equals 2 minus log of the percent transmittance. I'm just going to do the math quickly. My absorbance turns out to be 0.503. All right, there is my absorbance value. Does this make sense? Let's just double check and make sure this makes chemical sense. I have a very high absorbance. I have a very low transmittance. That makes sense. I've absorbed a bunch of energy, only 9.1% of it. I have about half the absorbance and I have more light getting through. That makes sense. Absorbed a lot of light, absorbed less light. Absorbed a lot of light, absorbed less light. So those things do actually line up. Now I'm going to plug this into the equation above. Again, same idea. Instead of so again, I'm just going to rewrite this equation because I'm going to need it below anyway. Absorbance is equal to 2084.1 concentration of FeSCN 2 plus 0.0127. Now I do the math. So 0.503 minus the 0.0127. Great. Divided by 2084.1. Boom. End up with a concentration of FeSCN2 plus equal to 2.35 times 10 to the minus 4. There is my concentration. So the absorbance is lower, meaning this concentration should also be lower. And it is. 5 times 10 to the negative 4, 2 times 10 to the negative 4. So lower absorbance, lower absorbance, lower concentration. This does, in fact, make chemical sense. All right, maybe I don't have to do the next one on the fly because hopefully I got this one right. All right, a solution is prepared by mixing 25 times of 0.002 molar KSEN and 225 and 0.2 iron. Okay. Calculate the expected concentration. Calculate the expected concentration of FeSCN, assuming the reaction forming complex ion is completely to the right. So we can assume that there is no equilibrium here. We just get all products. So this is not a question of using any lab data. This is just simply me saying, okay, imagine the reaction goes. By the way, this is how your calibration curves are done. The concentration of the iron is massive. Look at this concentration difference, 0.2 versus 0.002, right? That's 1,000 times different, right? 100 times different than, right, 1, 2, 3, 1,000 times different, 1,000 times more concentrated iron than the KSCN. So I have a ton of iron. Not to mention I have more, it's 1,000 times more concentrated. I also have a lot more of the iron in terms of volume. So we can assume that the iron is in excess. That means that the KSCN is limiting. All of the math that we're going to do is going to be based on the KSCN then, because we don't have to worry about the iron. There's enough iron there to go around. So whenever we're doing one of these, whenever we're doing asking a question about iron, in this case, I'm asking a question about the concentration of iron, but I'm not given information about this complex. So I have to use stoichiometry. If we're using stoichiometry, we need to write out an equation. I'm going to put a one-sided arrow because this is one direction. There is no going back. It is in such high concentration that we can assume that it's all product. Because KSCN or SCN is limiting, we're going to use the information from SCN. So I'm going to start with 25. And so we're going to do some dimensional analysis. I want to figure out how many moles of SCN, because for every 1 mole of SCN, I'm going to get 1 mole of FeSCN. We're assuming it's a 1-to-1 because it is a 1-to-1 and it's going to completely go to product. So if I have 25 mils of KSCN, I want to get rid of the mils. Actually, I'm just going to put liters and moles here for a second. The concentration of my KSCN happens to be 0.002. Yes? Good. 0.00200 moles per 1 liter. If I want liters to cancel, hopefully this doesn't go too far over your heads, but I'm going to actually, if I put the same metric unit prefix in front of both of those, it's still the same ratio. Moles to liters is the same thing as millimoles to milliliters. Using millimoles helps us simplify the numbers so I don't have to have, but this is going to work out. Trust me on this. So milliliters is going to cancel, leaving behind millimoles. And this was of KSCN. Once we have moles, or millimoles in this case, I can now do a conversion. For every 1 mole of KSCN, I have 1 mole of iron thiocyanate, right? This is my molar ratio. Again, I can just put a milli in front of that to make sure the milli cancels there. And it's all going to make sense as to why I did this in a second. So if I do this math, I find out that I have 0.0500 millimoles of iron thiocyanate. So I end up with 0.05 millimoles of KSCN. All of it turns into product, and we have 0.05. But that wasn't the question. The question was, hey, what is the expected concentration? So concentration is going to be moles per liter, or in this case, I know millimoles, and therefore I'm going to need milliliters. So in this case, I have 0.0500 millimoles all over how many milliliters? Well, 250 total milliliters. This is the total volume. Remember, it was diluted, although we didn't really include it. That 225 plus the 25 gives me a total of 250 mils. The concentration of my iron thiocyanate is going to be 2.00 times 10 to the minus 4, and it should be molar. There we go. Problem solved. All right. That's it. Easy enough. Moving on. All right. Based on your calculation, what is the expected absorbance? We're going to be using the absorbance equation a little bit backwards here. So absorbance is equal to 2084.1. Again, you should be using your own absorbance equation plus 0.0127. I'm going to I'm going to plug in my concentration of 2.00 times 10 to the minus 4 molar and do the calculation, right? Just do this math. You should end up with a concentration of 0.430. And that does line up with what we saw above. So it's pretty close to what we saw above. Calculate the expected transmittance. Okay, we can do that. Easy enough. Absorbance is equal to 2 minus the log of percent transmittance. My absorbance value of 0.430 equals 2 minus log of percent transmittance. Okay. I'm going to subtract 2 from both sides. So I end up with negative 1.57 equals negative log of the percent transmittance. I'm going to negate both sides. So you end up with 1.5. Move it over here, actually. 1.57 equals log of the percent transmittance. And then I get rid of the log by raising both sides to 10. So 10 raised to 1.57. The percent transmittance is 37.2%. So you should get something close to that. There we go. All right, problem solved. So that's it. A lot of moving absorbance and transmittance. We use absorbance because it's linear. Transmittance is not quite as nice. So that's why we do it. All right.